Hello again. This is the notes and assignment for the third part of this unit on piecewise functions. I did do a video on how to enter piecewise functions in your graphing calculator, although that is not needed on this assignment. It's good to have the knowledge, and maybe at the end I'll grab the graphing calculator and put one of these in, and you can have a nice little review of entering piecewise functions on your graphing calculator. All of these can be done without a graphing calculator. Also, there's not a separate notes document and assignment document. I'm going to do these few problems on here, and then the rest are for you to do. I think it's simple enough to just approach things that way. So on 1, 5, and 9, this is very simple. You're going to locate the piecewise function that you're using and then substitute in for x that particular value, but you need to figure out what part of the piecewise function you're going to be using. So f of 2 means go to the f function right here, and x is 2. So we're in the bottom line as far as the function goes. So this just equals 2. And remember, this means the coordinate 2, 2. And usually there's an x to substitute in for. There's not in that function. It's just 2. Number 5, g of 7. So we want when x equals 7, which is the bottom line. So we're going to do 2 times 7, 14, minus 1, 13. So in that one, you had a x to substitute in for, h of negative 4. So over here, it's the top one. X is negative 4 in the top line because it's less than or equal to negative 2. And so you do 1/2 times negative 4. That's negative 2. Negative 2 minus 4, negative 6. So pretty simple on function evaluation in piecewise functions. You just need to figure out what part of the piecewise function you use. On 13, 14, and 17, you are trying to match up the graph with the function statement. And what I'm going to tell you to do is don't try to grab your graphing calculator and figure out how to enter every one of these. That's not the best way to go about this. Look at the cut point. So the cut point here is 1. Cut point here is 0, negative 1. And then which one of these graphs has cut points at 1? So we'll start with 13. So what is meant by that is where the graph comes apart, or where the graph starts to go into the other graph. So you see on A here how at 1, there's that jump. So these are scaled by 2, so be careful with that. So A is a possible answer to 13 because it cuts at 1. What's another graph that cuts at 1? D is another one. So you see at 1 here, the jump at x equals 1. Also, E is one that cuts at 1 with that big jump. So that's the first thing. Decide what possibilities. So A, D, and E are possibilities for 13. The next thing is to look at y-intercepts, and that just pretty much sums up everything, if you can see the y-intercept. So I know I've got y-intercept of negative 4 here. This top one is going to be where the y-intercept happens. Bottom one would be 0, but it's not extended. The graph's not extended. So this is the only one here that has a y-intercept of negative 4. These other two, this is negative 2 and that's 0. I can just eliminate it based on that only. The y-intercept of either one, depending on which part of the function it's located on, and then the cut point. 14, the break is at 0. That's the y-axis, so B and D are the two that break at 0, x equals 0. Well, I know immediately the answer is B because I'm looking at y-intercepts of 4 being the same, so it's actually going to come together. Both y-intercepts are 4 and on that part of the graph. So B is the answer on 14, and I didn't say 13 was E, sorry. I need to write down the multiple choice. And 17, the break is at -1. So we're looking at C, only C. Well, that's easy. That was no fun. So only C here, because the break is at -1. It's the only one that has the break at -1. So that settles that case. So you have the other three to do where the breaks are at 1 here. So there's two choices, and then one that breaks at 0. But different y-intercepts there. Okay, so this one actually broke at 0 here. So there are actually two cases for 14. But that's the way to look at it. Where it breaks, that's in the domain description that I have highlighted, and then the y-intercepts, and it becomes pretty simple to do. Okay, last problem. So what you want to do when you're graphing a piecewise function is to start at the cut point. So the cut point is 3, and I know I'm going to have 2 open circles because I'm not including 3. And then substitute the x value into the function, even though we're not including it. So if I put 3 in here, I get 4. So I know 3, 4 has to be an open circle. We're not including it. And then 3, 6 minus 4 is 2. So 3, 2 is an open circle. And then we just have to figure out which way is our line, or our lines going. Well, the top one is for less than 3. So I've got to start substituting in points less than 3. So like 2. And so 2 plus 1 is 3. So 2, 3 is a point. And then you can start getting the idea of how this is going to look. There it is. That's just a line the rest of the way. You start at the cut point and you go. Do piecewise functions get harder than this? Yes. Knowing how to put it on your graphing calculator would really help if they start getting a lot more complicated. So greater than 3 now, so 4. So if we put 4, 8 minus 4 is 4. So 4 gives me 4. And so it looks like an up 2 over 1. You could use the idea of slope too. That's a whole lot easier probably, to be honest with you, because it's a linear function. What's going to happen on 21? You're going to start at the cut point of 3. 3 is the cut point. You're going to have endpoints to deal with. So you're going to have to substitute in the -6 here and the 6 here. And so it's going to stop at endpoints. And it's going to look like this. I'll show this. This is the answer key. You're not going to be able to graph -6, -22. So just a little there. But on this right-hand endpoint here, x is 6. 10 minus 6 is 4. So 6, 4 is open there. So I have this arrow. I needed to show this because it's this left-hand endpoint, again, is off the grid. -6, -22. It would be a solid circle at -6. 1, 2, 3, 4, 5, 6, -22. You'd have a solid circle on that. So they would appear as segments. So there's the other side of this. If you have endpoints, like these double inequalities, you have to actually graph that point as an endpoint, open circle or closed circle, by substituting in these values. So again, on the right here, we put in 6. 10 minus 6 is 4, and then an open circle there. It's just that the left-hand one, again, is off the grid. All right, so that is your lesson on piecewise functions. They're very simple, and I said I was going to do this. Let's quickly do one of these, and look at the video for a complete explanation. Yeah, I think that's good. So what you're going to do real quickly here is you're going to put in the top one in parentheses, then you're going to divide by, again, you're going to have to look at the video to understand this because I'm going to go pretty fast. You're going to divide by x is less than or equal to 1. And so how do you do that? you go second test. Test is behind the math button. And then less than or equal to, which is 6, and then 1. And what that is doing, as you'll see in the video, this means, so when this is false, it puts a 0 in there. And you can't divide by 0, so it just leaves the graph blank and it puts an error on the table. Simple enough. It's just a simple algebra type of programming type of language that it deals with. So 3x is then divided by x is greater than 1. So second test, we want greater than, so 3. Oops, I didn't put x first, sorry. So second test, you got to put your x first, is greater than 1. Okay, so there's the double inequalities, which I'm not doing an example of. You need to look at the video for those. And now this should give you something that looks like E. It doesn't show the open circle, solid circle, but it shows the idea. Okay, so that's a quick review, but look at the video for entering piecewise functions and how to use your table with it.